Great. Okay, so the next speaker is Yichul Choi from Stony Brook University, and he will tell us about non-invertible Gauss law and axions. Please.
First, I'd like to thank the organizers for having me here. I'm very happy to give a talk here. And I'll talk about my recent work in collaboration with Lam, who is at MIT, and Shuang Xiao, who is my advisor at Stony Brook. And there is another very closely related paper by Yokokura. And if you are interested, please check out both of the papers. So let me begin by something that everyone is familiar with, which is just the usual electromagnetism. So in ENM, one of the first things that we learn is the Gauss law. So the Gauss law says that we can measure the electric charge of a particle by surrounding it with a closed surface, say sigma, and then integrating the electric flux through this surface. In my convention, the Gauss law looks like this. But importantly, the shape of this surface is not important. The Gauss surface is topological. And as you know very well, this is because the electric field is divergence-free away from charged particles. So in quantum fields theory, this electric particle is represented by the Wilson line. So this is the world line of this probe particle. And this topological Gauss surface corresponds to the following topological surface operator, which I denote as Q of sigma. So in QFTs, whenever you have such a topological operator in your theory, it is a useful viewpoint to take to identify such a topological operator with some global symmetry in your system. There are many reasons for this. So first of all, these topological operators, just like any other ordinary symmetries, oftentimes lead to selection rules on your correlation functions. And they are matched under RG flows, and there are many other reasons. And I will show some of the examples later in the talk. So this will be the viewpoint that I will take throughout this talk. Any given topological operator on my QFT corresponds to a global symmetry of the system and vice versa. So in the previous ENM example, we had this topological surface operator Q of sigma, which should correspond to a certain symmetry of ENM. To be more precise, I will obtain the symmetry operator U sub alpha by exponentiating this charge as usual. This alpha is the U1 group parameter. But there is one difference from ordinary symmetries, which is that this topological surface operator naturally acts on Wilson lines instead of local operators. So this kind of symmetries that act on line operators instead of local operators are called one-form symmetries. So in the context of ENM, this U sub alpha is usually referred to as U1 electric one-form symmetry because it measures the electric charge of Wilson line through the Gauss law. Okay, now I want to move on to the main topic of today's talk, which is the axion-Maxwell theory. So this is a 3+1D QFT with this Lagrangian. So here, theta is a 2-pi periodic scalar field, and F is the field strength for the U1 gauge field. The first term is the kinetic term for the scalar field, and then the second term is the usual Maxwell kinetic term. Then the third term is important. It tells us how this scalar field is coupled to the gauge field. So such a periodic scalar field which couples to the instanton density of the gauge field is generally called an axion. And this axion-Maxwell theory with the U1 gauge group is really the simplest axion model that you could write down. It has many interesting properties and many generalized global symmetries. So axions were originally proposed as a solution to the strong CP problem, and they have many final implications. However, in this talk, I'll be interested in the more formal aspect of the theory. I want to ask what happens to the Gauss law in this theory. This is indeed an interesting question because the ordinary Gauss law does not work in the presence of axion. In the language of generalized global symmetries, what this means is that the electric one-form symmetry is explicitly broken by the presence of the axion. So if you look at the equation of motion for the axion-Maxwell theory, then the electric field is not divergence-free anymore. So my Gauss surface will not be topological anymore, and I cannot measure the charge of a particle using the ordinary Gauss law. So in a sense, you could say that the Gauss law is anomalous in the axion-Maxwell theory. Indeed, this is not a surprise, and this is actually totally expected because there is a Witten effect. Let me remind you that the Witten effect says that when you have a U1 gauge theory with a non-trivial theta angle, a magnetic monopole carries an electric charge which is proportional to theta. In axion-Maxwell theory, you should view it as a U1 gauge theory where the theta angle is promoted to the dynamical axion. More concretely, you can think of this kind of a thought experiment in axion-Maxwell theory, which will seemingly violate charge conservation. I can consider an axion string. So axion string, as you know very well, it's a one-dimensional object in space. And as you go around this axion string, theta will be shifted by, say, 2 pi. So what this means is that we can bring a magnetic monopole and then let it travel around the axion string. And it will experience the Witten effect, and it will freely gain an electric charge. This looks like it's violating the charge conservation. This is really the physical reason behind why the ordinary Gauss law does not work in the axion-Maxwell theory. But you can still define another quantity, which is topological and conserved. So let me rewrite the equation of motion in this following way. Now you see that this new quantity inside the parenthesis is divergence-free. So using this, I can define a new surface integral, which I denote as Q sub h, given by this expression. This new quantity is usually referred to as phase charge. And if you look at the expression, the first term is the usual electric flux. And then the second term is there to cancel the Witten effect, essentially. This new charge is formally conserved. And as before, I can exponentiate this charge and then obtain this U-head operator, which would be formally topological. However, there is a big problem with these operators, which is that they are not gauge-invariant. To be more precise, they don't respect the 2 pi periodicity of the axion. So can you do any better than this? So I'd like to have something that is both topological and gauge-invariant. This is actually possible. So for that, let me first restrict my group parameter to be some rational angle. And to take my U1 group parameter alpha to be 2 pi times some rational number, E over n. And here P and N are some co-prime integers. So this U-head operator at this value of alpha looks like this. And it is not gauge-invariant because of this red term. To be more precise, this red term is not gauge-invariant because the level is not properly quantized. So in my convention, this theta F coupling would be gauge-invariant if the coefficient is I over 2 pi times an integer. But instead of an integer, I have a fractional number here. However, this kind of fractional coefficients actually widely appears in condensed matter physics. Moreover, in that context, there is a well-known way to fix this non-gauge invariance. So in more detail, this kind of improperly quantized effective actions often arise from the response of a topological quantum field theory to external fields. So the most famous example of this is the fractional quantum effect. So in the low energy limit, it's a certainty QFT, and its response to the external ENM field is fractionalized. So we can apply this general idea to our situation. So this red expression, which was not gauge invariant, can be actually realized as a response of the 2D GN gauge theory, which I wrote in blue here. In this blue expression, this phi is a 2-pi periodic scalar field. C is the U1 gauge field. And this first term is the Lagrangian for the 2D GN gauge theory. And the second and third term, they tell us how the GN gauge theory is coupled to the external fields, which are in this case the axion and then the electromagnetic field. So now you see that this blue expression is perfectly gauge invariant. All the coefficients are properly quantized. Heuristically, you can go back to the red expression by illegally integrating out this little c gauge field. But the real viewpoint that you should take is that you should forget about this red expression. It's not gauge invariant. This blue expression is really the precise way to express such a improperly quantized response action. So motivated by this, let me define a new surface operator in the axion-Maxwell theory, which I denote as dp over n. This dp over n is obtained from the previous U-hat operator by replacing this red non-gauge invariant expression by this blue expression, which was perfectly gauge invariant. So here, phi and c, you should think of them as auxiliary fields living on this surface operator, which are there to cancel this non-gauge invariance, essentially. So now this new operator is both topological and gauge invariant. So it defines a good surface operator in my theory. And since it's topological, I should view it as some kind of symmetry operator. And it's a surface operator, and it's a naturally acting line operator through linking. It defines a new one-form symmetry in the axion-Maxwell theory, which was previously not known. However, this new topological surface operator, dp over n, does not obey any ordinary group multiplication law. In particular, this operator does not have an inverse in a general topology. This kind of topological operators without an inverse are called non-invertible symmetry in these days. And such non-invertible symmetries have been really extensively studied in the past years. And this dp over n gives another example of a non-invertible symmetry. So let's rewind a little bit where we are. So we started from the ordinary ENM, there was topological Gauss surface. But if we add on axion, then the surface was not topological anymore. But we could define another topological surface operator by dressing the naive Gauss surface by the two-dimensional GN gauge theory. And this was this dp over n surface operator. And now let's try to use this new topological surface to measure electric charges of particles, just like ordinary Gauss law. Let's begin from the simplest case, where the particle does not carry any magnetic charge and only carries some electric charge. So we'll have a Wilson line extending in the time direction. When you surround this electrically charged particle with this dp/n surface, you can show that its action on this particle is exactly the same as the ordinary electric one-form symmetry. And I obtain this phase vector, which is just a standard phase vector from the electric one-form symmetry. To be more precise, if I do this measurement with given P and N, I can measure the value of electric charge Q modulo N. And then by doing this for different coprime pairs of P and N, I can completely fix the electric charge of the Wilson line. However, we expect the situation to be more complicated if we do it for a magnetically charged particle. We will have a tube line in this case. To be more concrete, let's say we have a particle with magnetic charge M and electric charge Q. So this will be a dione. The electric charge of the dione has a certain ambiguity because of the Witten effect. So if I shift my axion field by 2 pi, then the electric charge of the dione will be shifted by its magnetic charge because of the Witten effect. So the value of Q is well defined only modulo M. And indeed, this new topological surface operator precisely measures this value of the electric charge modulo M. Let me first tell you how dp/n acts on this dione and then try to explain what it really means. So I'm acting this dp/n on this dione. And if this big N does not divide the magnetic charge little m, then it simply annihilates the configuration. So it results in a vanishing correlation function. On the other hand, if this big N divides the magnetic charge little m, then it measures the electric charge just as usual. So I get this standard phase vector. What this means is that by using different coprime pairs of P and N, I could measure the value of electric charge Q modulo M, but I cannot do any better than that. This is precisely what we expect from the Witten effect. So intuitively speaking, this non-invertible Gauss surface always tries its best to measure the electric charge of the surrounded particle. And it always gives us the best sensible answer. However, when this is really not possible and it fails to assign any unambiguous value for the electric charge of the surrounded particle, it sort of give up and then just spits out number 0. So in a sense, this non-invertible Gauss surface kind of behaves like some smart machine or something. And we call this the non-invertible Gauss law in the axion-Maxwell theory. And this is really the punchline of today's talk. In the remaining time, let me tell you about some of the other implications. So we said that the topological operator dp/n defines a non-invertible one-form symmetry in the theory. It can actually show that, just like ordinary symmetries, it imposes selection rules on correlation functions, such as the one shown in this figure. I'm not sure if I have time to explain this during the talk, but if there is any interest, I will be happy to say more about this selection rule after the talk. And we can also make a connection to various conjectures in quantum gravity related to global symmetries. So in quantum gravity, there are 2 pieces of law. One is called no global symmetry conjecture. It says that there is no global symmetry in any theory of quantum gravity. And there is completeness hypothesis. It says that the spectrum of gauge charges must be complete in quantum gravity. And these 2 statements are often related And in some cases, they are even equivalent. For instance, if you consider the U1 gauge theory without an axion, then completeness is equivalent to no electric one-form symmetry. The reason is because if the spectrum of U1 gauge charge is complete, then what it means is that every Wilson line can end on a dynamical particle. We say every Wilson line is endable. If every Wilson line is endable, then obviously there cannot be any topological surface which can topologically link with a Wilson line, because you can always unlink this surface through this endpoint of the Wilson line. Another way to say this is that if you have dynamical charged particles, then the electric charge of the Wilson line is screened by the dynamical particles. And then your Gauss surface will not be topological. However, when there is an axion, the equivalence between the completeness and then no invertible electric one-form symmetry breaks down. Indeed, we saw that in our axion-Maxwell theory, there was no invertible electric one-form symmetry, even though the spectrum is just empty. There was not a single dynamical particle which was charged under the gauge, which carries some gauge charge. However, now we see that this equivalence is restored if we include the non-invertible electric one-form symmetry to the conjecture. The argument is essentially the same as before. If the Wilson line is endable, then my surface cannot topologically link with the Wilson line. So more generally, it is argued that the no invertible and non-invertible topological operator is equivalent to completeness. And then this is another example of that. Okay, with that, I'll end my talk, and thank you for your attention.
Thank you very much. Are there any questions? Maybe I can start with one. So I would say for the completeness in a quantum gravity, also the magnetic states play a role. So I also don't want the magnetic one-form symmetry left over once I go to the quantum gravity theory. Now, while your non-invertible one-form symmetry sort of measured the electric charge in a smart way, but had problems with the magnetic charge, my question would be, do you have any idea what completeness would look like for magnetic charges for these non-invertible symmetries?
Yeah, so I guess in the axion-Maxwell theory, it's more standard for magnetic charges. So this theory has the magnetic one-form symmetry, which is just invertible, usually one magnetic one-form symmetry. And yeah, it will be broken if we include dynamical monopoles.
And so my question was just if you use the non-invertible object that measures the electric charge, it also measured something in the magnetic sector, right? So if you surround
actually, that's a good question. So actually, another thing is that in this axion-Maxwell theory, there are, I guess, many ways to break this non-invertible one-form symmetry. We can just add electrically charged particles. Or actually, if we include dynamical monopoles, then first of all, it breaks the magnetic one-form symmetry, but it actually also breaks this non-invertible symmetry. Yeah, so there is a certain hierarchy of these symmetries. So yeah.
Right. I see. Because of the Witten effect, basically you say if you throw in monopoles, it's enough to break almost everything unless there is some integer number that produces. Okay, that's very cool. Okay, thank you very much.
Exactly, yes. Thanks.
Other questions? Yes, Bruno.
Hi, thank you for the talk. Just a somewhat random question maybe, but so this idea of having a conserved current, which is not gauge-invariant, or maybe a gauge-invariant current, which is not conserved, reminds me of the U1 problem in QCD, where you have the anomaly, and there the solution uses instantaneous, and it's completely different from what you do. But do you think there is any analogy beyond this very basic observation?
Oh yeah, for sure. So actually, we had an earlier paper about precisely this. So it's the same set of authors. It's this paper. So let me consider maybe an even simpler example. Let's just do a QED with a single charge one Dirac fermion. And you see that there is if you consider the axial symmetry, then there is an ABJ anomaly. So the axial current is not conserved. But you can actually promote this to a non-invertible axial symmetry by essentially applying the same trick. So the naive axial symmetry operator, so it will be a three-dimensional operator. It is not topological, but you can address this three-dimensional surface with a certain TPFT and then make it topological again. And it will become an exact non-invertible axial symmetry in QED. And also in QCD in below electric weak scale in the massless limit.
I see. Thank you.
Thanks.
Are there any other questions? Yes, Guillermo.
Yes, I have a question. So at some point you discussed the action of this non-invertible operator, and it's zero when you cannot, where there is issue with the Witten effect. So is intrinsic to the fact that you have this Witten effect, or is this generic of non-invertible symmetries that they act like non-faithfully, like they?
Yeah, this is kind of this is kind of a general feature of non-invertible symmetries. It usually annihilates certain configuration or certain operators. And
is this understood on a systematic way, or is it just observation that in many cases it seems to work that way?
Let me see. I'm not sure if there is a general proof for this. Yeah, but it's, in many cases, it's true. I guess, yeah, I should say it's an observation.
Okay, thank you very much.
Thanks.
Any more questions?